Welcome to part 3 of our lecture series on the fundamentals of data science and machine learning, focusing on regression. In the previous lectures, we've laid the groundwork by understanding the basics of data science, explored data preparation techniques, and introduced the concept of machine learning. Now we delve deeper into one of the most critical and widely used techniques in predictive analytics, regression analysis. Regression is a powerful statistical method that allows us to examine the relationship between two or more variables of interest. It's the backbone of many predictive models, enabling us to forecast outcomes, understand the impact of different variables on a target variable, and make informed decisions based on data. By the end of this lecture, you will have a solid understanding of regression analysis, equipped with the knowledge to apply these techniques to solve practical problems in data science and machine learning. Whether you're analyzing customer data to drive business decisions, forecasting economic trends, or building predictive models for scientific research, mastering regression will be a valuable skill in your toolkit. Part 3. Regression Analysis in Data Science and Machine Learning. Introduction to Regression Analysis. Regression analysis is a statistical method used for modeling the relationship between a dependent variable, target, and one or more independent variables, predictors. It's primarily used for prediction and forecasting, where its ability to identify and quantify the relationships between variables is particularly valuable. Why regression? Prediction and forecasting. Regression can predict the value of the dependent variable based on the values of independent variables. Insight into relationships. It helps in understanding how the dependent variable changes with variations in independent variables. Decision-making. Enables data-driven decisions by quantifying the impact of variables. Types of regression techniques. Linear regression. Models the linear relationship between the dependent and independent variables. It's the starting point for regression analysis. Logistic regression. Used for binary classification problems. It predicts the probability of the target variable belonging to one of the two classes. Polynomial regression extends linear regression to model nonlinear relationships between variables. Ridge and lasso regression techniques used to reduce model complexity and prevent overfitting by introducing a penalty term. Decision trees and random forests. Though not traditional regression models, they can be used for regression tasks, modeling complex relationships through a series of decisions. Regression analysis is a cornerstone of data science and machine learning, providing powerful tools for prediction, understanding relationships between variables, and making informed decisions. By mastering regression techniques, you can unlock valuable insights from data and apply these insights to solve real-world problems. In the expansive landscape of data science and machine learning, tools and methodologies evolve to address specific needs, often overlapping with business intelligence disciplines. Let's delve into the core aspect of this domain, regression analysis. The role of regression in machine learning. Regression is pivotal in the modeling and evaluation phases of machine learning. Its essence lies in deciphering the relationship between independent variables, predictors, and a dependent variable, target, typically continuous in nature. Through regression, we aim to outline this relationship, often visualized as a line of best fit, enabling us to predict the target variable's value based on given inputs. Understanding linear relationships. At the heart of regression is the linear relationship model, where we explore the interaction between a single predictor, x, and the target variable, y. This relationship is encapsulated by the equation I equals mx plus c, where that represents the target variable we seek to predict. X is the predictor variable. M denotes the slope or coefficient, indicating how much y changes with a unit change in x. C is the intercept, signifying the value of y when x is 0, though its interpretation may vary depending on the context. The slope M provides insights into the nature of the relationship. A positive M suggests a direct relationship, whereas a negative M indicates an inverse relationship. The magnitude of M reflects the strength of this relationship. Expanding to multiple linear regression. Real-world scenarios often involve multiple predictors influencing the target variable. Multiple linear regression extends the concept to accommodate several independent variables, x1, x2, xn, enriching our model's predictive capacity. The equation evolves to I equals 0 plus b1x1 plus b2x2 plus bxn plus e, where each xi has an associated coefficient by and e represents the error term. This model is more complex, visualized not as a line, but as a plane or hyperplane in higher dimensions, encapsulating the collective influence of all predictors on the target variable. Regression in practice. Regression analysis serves as a foundational tool in data science and machine learning, offering a window into the intricate dance between variables. Whether through simple linear regression or its multiple counterparts, it equips practitioners with the ability to forecast outcomes and unearth insights from the vast data landscapes, navigating through linear and nonlinear relationships alike. As we harness regression in various applications, from predicting sales based on marketing spend to forecasting crop yields from environmental factors, it remains a testament to the power of data-driven decision-making. With each model, we inch closer to unraveling the complexities of the world around us, making regression an indispensable ally in the quest for knowledge and innovation in data science and machine learning. This concludes our exploration of regression within the realms of data science and machine learning. We've journeyed through the conceptual underpinnings of regression, from its role in modeling and evaluation to the intricacies of linear and multiple linear regression. By understanding these principles, we equip ourselves with the ability to analyze and predict complex relationships in data, a fundamental skill in the data scientist's toolkit. As we progress in our learning journey, remember that regression is just one of many methodologies employed in data science and machine learning. Each tool and technique has its unique purpose and application, contributing to our overarching goal of extracting meaningful insights from data. Whether you're predicting future trends, understanding relationships between variables, or building models for decision-making, regression offers a solid foundation upon which to build further knowledge. Stay curious, continue exploring, and let the power of data science and machine learning illuminate the path to discovery and innovation.